Hi everyone, good morning, good evening, good afternoon, depending on your time zone. My name is Alex and I will be your host for this short webinar on injecting chaos inside Kubernetes workloads. If you are here, maybe you have questions about what is SRE, site reliability engineering, what are SLAs, SLIs, and SLOs, and maybe you want to see and understand what they mean. And of course, what is the relationship between site reliability engineering and chaos engineering? And as you will see in the demo, they are hand in hand somehow, because at the end of the day, what we try to achieve, we want to have or to increase the resiliency. So what we are going to do in the live demo, we are going to run a small application deployment inside on top of Kubernetes cluster. And after that, we are going to see how we can create some policies which can kill randomly specific pods inside of our cluster and see if the application resiliency is still there, to see if the pods are still being created after we delete them and our application is still accessible from the outside world, because we want to minimize the downtime and we want to make our customers happy. This is the end goal. So let's get going. Again, a little bit about me. I'm Alex, system integrator working in different areas like DevOps and DevSecOps, and a tech enthusiast. Don't forget, if you want to learn more about DevOps, or if you are new to DevOps, please subscribe to our DevOps Artisan project, where you can see or join our trainings on different topics and in different areas, like configuration management, working with Kubernetes, monitoring Kubernetes. If you want to learn about Docker, everything you will find inside the DevOps Artisan. Of course, if you have other questions, don't forget to drop us a note on the email that is specified on the slide. By the way, at the end of the training, you will receive the recording and also the presentation. And also you will receive, if you join the classes, you will receive a discount, but everything it's on the email that will come after the training. Before we start, the last thing that I would like to tell you is, if you have questions, don't forget to ask them inside the chat, but I will try to answer them at the end of the training, the presentation webinar. Okay, so let's start with the first part, right? And let's start to understand SRE. So think a little bit. First, the first question is, what is SRE and what it is with this buzzword, right? So SRE stands for Site Reliability Engineering, right? So we have engineering. This means that are the people, the engineers who are doing the job done, right? Reliability sometimes can be used in the same way with the resilience. And site, you can do an analogy with a website or with a system or a service or a software. Or to be more generic, you can think that is that online stuff that is on the internet. So from another point of view, you can think that site reliability engineering can work across of anything as a service, right? You can think it's infrastructure as a service, software as a service, platform as a service. And what it tries to achieve, basically, at the end of the day, it tries to guarantee you the fundamental end user's expectation. And that expectation is to have the service, the application up and running. And of course, besides that, it has to be reliable. Of course, from another point of view, you can see that or think that SRE, it's a framework or it's a kind of model that can help you to run services in a more reliable way and tries to help you to view how to implement this, right? To implement reliability focused engineering work. Of course, everything started at Google. This SRE concept and framework was designed at Google around 2003, but started to become more popular, in the last 3 or 4 years. So what we try to achieve, the appropriate level of reliability of the systems, of the services, of the product. But the thing here is how we can do that, how we can implement these things, right? Because we want to have scalable systems, because we want to see and define the operational aspects of our services, of our workloads. We have to perform capacity planning on our infrastructure. And of course, we have to monitor those systems. And somehow we have to bring together the developer teams with the operational teams and all the time try to improve and try to automate all those manual steps that can be removed from our day-to-day work in order to focus on what matter most, on fixing reliable problems that we found inside our production environments in order to make sure that those problems will not happen again. And if they do, at least we can fix them in a matter of, I don't know, minutes, seconds, depending on the complexity of the problem. Why is that? Because if we minimize the downtime on the production systems, also we minimize the customer cases or customer escalations that can appear in this kind of scenario. But everything that it's related on SRE, it comes or builds on top of DevOps, right? We had a webinar in the past where we discussed a little bit about DevOps and what is DevOps. So the basic idea, or at least what you have to have in mind, is the following quote from Google folks. They said that class SRE implements DevOps. So it's built on top of that DevOps success culture paradigm, but it tries to achieve more. So as a site reliability engineer, folk who wants to work on reliability of the systems, we have to think that we cannot work or we cannot spend time on operational side or on the development side 100%. We try to split in some kind of proportion the work. So from the point of view of Google, they said that, at least from the point of view of their model, they said that 50% an SRE has to focus on the engineering problems like infrastructure, networking, databases, and here to improve the availability, to improve the observability of those systems, the efficiency, and of course, the reliability of those services. And also, the rest of the time, the other 50%, to focus on software engineering problems, right? So think about this. If you are an operations guy and you see a problem in a production system, and you know how to fix it, or at least how to troubleshoot it or to investigate it, why not also try to implement this inside the service application code in order to make the application more resilient on this kind of failure, right? So that's why it's important to work also on the software engineering problems, right? On the application design, on the data structure, and service design, and also integrations, right? Because working on this kind of performance scalability scenarios, you can improve to the reliability of these distributed systems, right? Because these days, most of us or most of the companies are trying to migrate from a monolith architecture to a microservice-oriented architecture. But also in a microservice-oriented architecture, we have different kind of limitations, problems. We have many systems, many kind of deployments on-prem inside the cloud. But the cloud can be between different kind of vendors, right? Like Amazon, like Google, like Oracle, and so on and so forth. So since we have this complexity also around building infrastructure and maintaining this kind of services in a multi-cloud environment, in a distributed system, also our skills or competency has to focus on also in the infrastructure side and also on the engineering, software engineering part of the problem in order to make those systems more reliable. So, what are the objectives in this case from the point of view of site reliability engineering? So, you have to think that an SRE engineer has to treat the operations like a software engineering problem. And this was a quote from folk from Google. I'm trying to find it and try to say it, but just give me a second. Stephen Thorne said something like this: SREs have the skills and the mandate to apply engineering to the problem space. A well-functioning SRE team must do operation mindfully and with the respect of their actual goal, helping the entire organization take the appropriate risks. And I ended the quote. So this is from Google, Stephen Thorne, in 2003, 2004. So everything in operations, it's treated like an engineering problem. So if it's a software engineering problem, this means that there must be a way to automate or to make the application, the code, more resilient to different kind of failures. The second part is to automate more, right? So here, SRE tries to implement or tries to assign or improve the automation rate, which is normally done by the system administrators, right? And here you can think that you need to remove the toil. So what is toil, right? Toil is something that is manual, that is repetitive, and that can be automated. Because if you remove these manual processes from your day-to-day work, you have time and you can focus on other problems, right? Like design, like architecture, coding more. Of course, don't think that if you are an SRE, you will do all day coding or you will do day operations. Why is that? Because SRE, it's something that you need to implement inside of your organization. And implementing it depends on on your organizational culture, let's say, right? So we cannot have one good solution that will fit all the cases. But the focus is to do this. Threat operation like engineering problems, automate more, and design more reliable and operable service architecture from the ground up and not after though. So remember that code, SRE implements DevOps, right? What SRE tries to bring to the table. Remember that DevOps, it's a set of principles and some culture guidelines that helps you to remove the silos between different teams, right? And it tries to reduce the silos, it tries to plan for failure. It's all about tooling and automation and tries to improve the monitoring inside your infrastructure. But SRE tries to build on top of that and give you a set of practices with the focus on the engineering side, right? In order to implement those DevOps practices. And of course, it depends by the role and the team. And in this case, it goes further and tries to reduce the silos in organizations where you have shared ownership between different departments, different divisions, and so on and so forth. Secondly, we still have to plan for failure, but we plan for failure with error budgets, and we have to make plans what we do when we get out of error budgets. Maybe we can stop the release or improve the software or improve the architecture, right? Thirdly, we do incremental changes inside our development workflow, but we do in small batch because we want to focus on stability. We do different kind of testings and different kind of pipelines in order to validate that a new build or a new commit didn't break the stability of our application, right? Maybe a developer commits some code and that code can trigger, I don't know, buffer overflow when it's deployed in production, right? And we need to make sure that those changes are reviewed properly by the entire teams, the development teams, the SRE teams, and those changes are also validated properly. I don't know, maybe using different kind of deployments, can do a blue-green deployment or a canary deployment in order to validate that everything works properly. Also, like I said, we need to remove the manual work, the manual tasks. So here, the engineers try to focus more on different kind of tools that can help them to automate more and to make their life, let's say, more easier at the end of the day. And of course, don't forget, we need to monitor everything, because if we have proper monitoring, we can detect problems in advance using different kind of alerting mechanisms or creating different kind of SLOs. And at least we can know that something went wrong, but didn't break the SLA. Don't worry if you don't know what is an SLO or an SLA, because we are going to discuss a little bit later about that. So, to sum up, it's all about embracing risk as an SRE function. We have to create our SLOs. We have to eliminate the toil. So again, toil, it's the automated, the manual part that can be automated. We need to perform monitoring for our distributed systems. We have to do more automation and release engineering, and we have to do everything with some kind of simplicity, because if we perform big changes inside of our infrastructure, inside or our environment, we can lose control, and the stability, the reliability of our systems can degrade over time. So now we have to think, and let's discuss a little bit about SLOs and SLAs, right? But let's start with this. A service level, at least, because everything is a service level, SLO, SLA, SLI, right? It's the foundational tool that an SRE team needs to function, right? So we have three here: indicators, objectives, and agreements. So let's see what is a service level indicator. So using an SLI, we can define a quantitative measure of some aspect of a level of a service, which we provide, right? This kind of measurements, because it's a measurement, the SLI, can be gathered from the server side or from the client side using monitoring and using log analysis of those systems. Because if we don't have monitoring and logging, we cannot define our measurement, our quantitative measurement, right? We cannot create our SLA. And of course, the second question will be, what are those measurements, right? Because every system, it's different in own way. So if you don't know from where to start, you can start always to use the 4 golden signals as a starting point. So you may wonder, what are those 4 golden signals? And here they are. We have latency, traffic, error rate, and saturation. So request latency or latency, you can think about something like this. How long does it take to service a request? How long it takes me to visit a website? If it takes too long, I will close my client browser, or maybe I will open a new browser and go into another website in order to buy something, I don't know. Traffic, how much demand is being placed on a system, right? So here you can think about this situation. If your website or your service will be under a distributed denial of service attack, your service will be still up and running. Think about this, okay? Error rate. How many errors, how many failed requests, or what is the rate of those failed requests on our service? And saturation, of course, it's how overloaded is the system. So these 4 golden signals are a great place to start for the most of the systems, of course. But depending on the use case, you can use other kind of SLIs depending on the needs and, of course, of the type of the system that's monitored, right? We can have databases, we can have networking devices, we can have load balancers, we can have compute instances, and so on and so forth. For example, think about a storage system. Maybe there you need to know about, you need to have an SLI for data durability and also system availability of that data storage, right? Good. So this is the SLI. Now let's go to the SLO. So the SLO, it's a target range of values for a service level, which is measured by the SLI, right? We create the SLI, and after that we create a measurement on a range of values using those SLIs. So with the SLO, or to put it otherwise, the SLO will be the most important kind of construct that the the site reliability engineer will use on day-to-day basis, let's say, because these values of the SLO should represent the acceptable behavior that a user or of that service should be experiencing, right? And of course, the SLO can be adjusted based on the needs of the company, of the organization, and of course, based on the expectations of the users. And lastly, we have the SLAs. So maybe all of us heard about service level agreements. It's the most well-known of the terms discussed so far, right? Because at the end of the day, it's an explicit or it's an implicit type of contract between the end users or the users which are using your system, your service, your application, your workload. And of course, depending on the service type, it is common to have some financial consequences if you breach the SLA, right? So SLAs typically usually require different departments, lawyers, in order to work on this kind of documents. So, what is the key takeaway from here? It's that you have to create some SLOs which are associated with the SLA. But the key takeaway is that the SLO should always be set to a higher tolerance than the SLA. Why is that important? Because let's say in a staging environment, you see that the SLO got out of the got a little bigger than the value that you set, but didn't break the SLA. This means that you have a margin where you have time to fix the problem or to roll back your change in order to not break the SLA. So basically, the SLO will give you a heads up on the problems that you have on your service, and it will let you know that something has changed and you need to investigate or take a look. Of course, we cannot continue or discuss more about this. This is just a short introduction. So if you want to learn more, please join the Site Reliability Engineering training course, and there we are going to find out new things about this. Or another key takeaway here regarding the SLO, and is the last one. You can think that the SLO is created from the SLI. You put a threshold and a time window, and in this way you create you generate the goal of that service. Of course, don't forget that 100% reliability won't happen, because if all those systems were 100% reliable, we didn't need to have this workshop, right? Everything was fine. And this is an example. By the way, I didn't manage to give you an example. So you can think that an SLA can be the HTTP request response time. So the SLI has to be lower than 300 milliseconds. You put a threshold of 90% and a time window of 1 month, and this will generate the SLO. This means that 85% or 90% of the HTTP valid requests should be less than the SLI, right? And SLI in this case, it's 300 milliseconds. And this percent has to apply to the average, and here the average, the time window, it's 1 month. And this is another one. So if you increase the SLO, you'll see that the time before objective failed will decrease drastically. So you have to make your system very, very resilient to failures. And before we close the discussion on the SLOs, SLAs, and SLIs, the next question will be why we need these SLIs, SLOs, and SLAs. Because will help us to manage our service properly. They will give us the right metrics, the right SLIs that really matter for us and for our customers. And with these SLOs, we can see if the service has degraded over time or not. And of course, we can define the level of acceptable of downtime. And in this way, we can improve our applications, our services, our workloads. And of course, end users will not complain about our products, depending on the use case. Okay, so until now, we discussed about what is SRE. But why do we need chaos engineering, right? What is the purpose for that? Or what is the relationship between site reliability engineering and chaos engineering, right? So everything starts from the fact that we are migrating, we are moving monolith architectures to microservices. But the problem is that every component in this distributed architecture will have an influence on the entire design of the applications, work service, or workloads. So what can happen? Think about this. You have an application in production and your application, it's redesigned to be in a distributed microservice architecture. And one of the, maybe the database microservice, it's down. This means that the end users cannot query, I don't know, the database and perform different actions on that specific endpoint. And overall, from the point of view of the entire architecture, nothing will work. If the database won't work, cannot return responses to the clients, so the clients will be disappointed. Or you can think other way. If the database doesn't respond, or maybe also the front end will increase, will have a timeout, and it will wait until the timeout will expire, and after that will return a response to the user. But if you have a timeout, this means that the latency will increase. And if the latency will increase, the user will be somehow disappointed because maybe he was expecting to get a response back in under 1 millisecond, and now he has to wait 5 seconds and still doesn't get any feedback from the application. So how we can make sure, or how we can validate or test somehow this kind of negative scenarios? We can use chaos engineering, right? So with chaos engineering, we can learn about how the system behaves by applying exploration, by conducting different kind of experiments, right? So you can think the same way as scientists are conducting different kind of experiments to study physical and social phenomena. In the same way, chaos engineering uses this different kind of experiments to learn or to understand better a specific system. And here, of course, a system can be anything, like a distributed system, like our applications, like our services, and so on and so forth. So let's take a look of some chaos experiments or some examples. Think about simulating failure of a region, of a data center, of a zone. Think about injecting latency between your services inside your microservice architecture and see how the traffic will behave. Decrease the number of the CPUs on your logging cluster or your monitoring clusters, or decrease the RAM and see how the system behaves. And if you are doing this kind of chaos experiments, you can prepare, or you can see how your system will behave in the worst case scenarios. Because let's be honest, things break and all the system will break one day. It's a matter of time when this will happen. So, of course, I didn't cover many things in the chaos engineering part because it's a new discipline and there is not a lot of concepts involved there, but this is not the purpose for this short demo webinar. So I think this is it from the point of view of the presentations. If you have any questions before I start the demo, please feel free to ask them inside the chat. If not, I'm going to work on the demo. So, like I said, for the demo, we have Kubernetes cluster. It's an OpenShift OKD cluster, as you can see here. And also I have an application, Hello OpenShift. Basic, simple application, nothing more, nothing less. So this is available on the public internet. I will scale the deployment. So I will do like this to show you that the application is there. So now it's working because we have pods inside the cluster, right? Okay. What I'm going to do now, I'm going to scale the deployment, and I'm going to scale the deployment to 0. And in this way, this will not work anymore. It will give me an error at a point in time. We have to wait until all the pods are down. Let's wait a little bit more. Okay, application not available. This is an error returned by the OKD cluster. So it gives you a few reasons, okay? So it's not working at this point. So going back to the command line, sorry, but I have to switch between command line and web UI because I have to show you different things. So let's make the application up and running. So the application, the workload, it's running inside Kubernetes and it's running inside the deployment, okay? The application is very simple. It's something like this. It's a deployment type and it's running Hello OpenShift using the Hello OpenShift image, and it's listening on port 8080. Of course, it's exposed to be accessed from the internet because that's why we have that URL. And let me scale it back. I will put replicas 30. So I have 30 pods running inside our deployment. kubectl get deploy. Watch. You see? Now it's creating all the pods. Remember, Kubernetes all the time tries to match or create the desired state by comparing with the current state using watches and controllers. Okay, this is the core function or the core idea behind Kubernetes. Or to put it otherwise, you can think that Kubernetes is something like a database, which is monitored all the time in order to using watches and controllers in order to maintain the desired state comparing with the current state. Okay, so we have 30 pods which are distributed inside the Kubernetes cluster. These pods are running on the worker nodes. In this case, are deployed on these 3 virtual machines. Of course, if you have more nodes, or if you have a bigger Kubernetes cluster, let's say, those pods from the deployment will be distributed all across the nodes. Of course, you can do some different kind of customizations. Think about this. Maybe you have a Kubernetes cluster into availability zones, right? Into regions, into zones. And you want to make sure that our applications are up and running all the time, right? So we have these 30 pods on 3 nodes for this example. And let's see if this is up. Hello, OpenShift. So it's up our demo application, okay? Nothing fancy here. Good. So let's see how we can inject some chaos on this application and see how the system will behave. So for this demo, I'm going to use a tool which is open source and which is called Powerful Seal. And basically with this tool, I'm going to create different kind of experiments from the point of view of chaos engineering, right? If you want to find more information about this tool, or if you want to use it in your cluster, Google it and Powerful Seal. It will give you a link to the GitHub repo. Okay, so what we can do with this tool? This tool is written in Python, of course, so it's very easy to learn and use. One mention that I want to let you know, it's the fact that, of course, are other tools that are proprietary or open source, but for this demo, I'm going to use this. It is also Litmus or Chaos Cube and so on and so forth if you want to take a look on the World Wide Web. Okay, so what we are going to do, we are going to inject some chaos. So with this tool, we can communicate with our Kubernetes cluster. As you can see, I'm in a Python environment on the Bastion hosts. So I cannot speak with the pods directly, but I have the configuration done. So I am able to query the Kubernetes API server because I have the proper credentials and the configuration. So let's take a look at the policy. Policy.yaml. It's declarative way, right? So we with Powerful Seal, we define the scenarios, right? So the scenarios, we are going to define what we want to do. So what we want to kill the pod, okay? So we have these steps: pod action, matches namespace nginx, filters random sample size 10, actions kill probability 1. Wait 10 seconds, and the third step is validate that after 10 seconds you have your pods recreated by the scheduler, by the cluster, by the Kubernetes cluster. And let's take a look of on the applications. Of course, our pods, get pods, are deployed YAML. And I want to show you that all of them are grep nginx, are deployed in namespaces nginx, okay? This means that we'll match the policy, right? Because the policy, it will go to only to the nginx namespace, and it will kill randomly 10 pods with the probability of 1. This means that it will definitely kill those. It's 100%. If you put lower, 0.1 or 0.5, the probability will decrease. But in order to be sure that are destroyed, we'll set them to 1, okay? The wait condition means that he will wait 10 seconds, and after 10 seconds, it will make sure that all the pods that we deleted are recreated. And of course, those pods are in running state, because as you can see here, we have the check pod state running. Okay, so let's see. I'm going to open a new split, and I'm going to do this. kubectl get pods o n nginx watch. Okay, and I'm going to run the script. How I do that? It's very simple. It's just one liner, and it's this powerful seal, and you have to specify the policy YAML file, right? So it's starting, and you will see that it will be executed, and we should see here. You see how fast it happens. It killed some pods, and of course, because Kubernetes always compares the desired state with the current state, it will create new ones, right? So it created back our 10 pods. And meanwhile, we have different information here on the powerful seed. Look here. It started the script. It took my kubeconfig file. It went to the namespace nginx. He found there that we have 30 pods in the nginx namespace and killed randomly some pods. See, pod killed. And you saw also in the demo that some pods were deleted here. You saw they were in terminating mode. So here we have different information about what pod killed and the IP addresses and different other third-party info. And after that, after he deleted all the pods, he waited 10 seconds. I think I skipped that part, and performed the validation and verified after that. You see, look here, sleeping for 10 seconds and verified that everything was fine. And after that, it's still continuing to work. It's sleeping 29 seconds and it's applying again the experiment. In this case, delete a pod or delete 10 pods and make sure that after 10 seconds, all of them are recreated. So what this means? This means you can create different kind of SLOs and you can create different kind of validations, right? Maybe you want to test your production system to see how it behaves. Or maybe you want to test your Kubernetes cluster to see how it behaves. Think about you have a multi-control plane deployment of Kubernetes, and you want to check what happens if the ATCD cluster goes down. What you have to do? You have to delete the ATCD. You have to delete the pod, which is running the ATCD cluster, right, in a random way, and see if the cluster it's still working. It's still up and running. Of course, don't do this on ATCD cluster in production. Do it on staging environment and make sure that everything is configured properly. You have backup strategies in place and you can recover very fast. Because if you don't have the ATCD database, in this case, this means that you cannot not longer check the desired state and compare it with the current state. And sometimes this can be a problem, can kill your Kubernetes environment. But if you are up and running for production testing using Chaos tools, you can do that with a powerful seal. So also, because we declare YAML files, this means that we can put them in an SEM, right? We can put them in Git. We can make commits, and based on commits, we can put it in a pipeline and deploy them at a specific moment of the day or a specific time to run automatically, right? And we don't have to run this manually like I did, if we try to apply the site reliability engineering principles. So yeah, I think this is it also with the demo. I can do another thing. I can scale it more. I will put to 50 and I will put the deployment. So the deployment is 50 and let's do experiment now on the policy YAML and put, I don't know, put 30 and apply this. Okay, and move on here and see what is happening. Again, we should see a lot of pods going up and down and other creating. Yeah, and in this way you can validate that your workloads are back up and running in a matter of seconds. You see, it took around 8 seconds for each one of them to be up and running. So 10 seconds, after 10 seconds, all of them should be back up and running. So the test, the experiment should be with success. If I am trying to decrease the experiment time, if my expectations are that the pods should be up and running after, I don't know, 1 second, this will fail. The test will fail, the experiment will fail, because it will not happen. It takes some time to recreate the pods, right? So you see, we have a failure information. Expected pod state running, got container creating, right? So it failed the experiment in this case. Okay, I will stop here. Thank you very much. I hope you enjoyed the session. Thank you and have a nice evening.